This research was inspired by an interest in appropriate and innovative systems that utilize low residue cover crops, like forage radish, to protect and feed the soil, and also to simplify spring cover crop residue management in short season production systems. In the Northeast, our cold, wet spring soils and our short summer growing season can make it really challenging to manage cover crop residue to mediate soil nutrients. So the question is, can we use winter-killed cover crops, including forage radish, to scavenge residual nitrogen in the fall, to protect the soil over the winter, and then to recycle nitrogen to the following crop in the summer? And can we do that while broadening the benefits of cover crops by including multi-species mixtures or cocktails? So in the Northeast, farmers plant about 5,000 hectares of sweet corn each year, which provides a substantial opportunity to research innovative and sustainable production systems for this second largest vegetable crop. This project evaluated winter-killed cover crop mixtures. You can see the table on the left, including peas, oats, forage radish, and all planted by September 1st in a no-till sweet corn system. We found that these cover crop mixtures provided valuable nitrogen cycling services by accumulating an average of 90 kilograms of nitrogen per hectare before winter kill in November. And in spring, the cover crop residue decomposed and provided startup nitrogen for the sweet corn, making it possible to eliminate at planting fertilizer, nitrogen fertilizer, which reduced both the cost of fertilizer inputs and also the risk of spring nitrate leaching. Cover crop residue did not reduce spring soil temperatures, which was really a significant concern of growers. Sweet corn yield following the cover crops was between 13 to 26% greater following these cover crops than after no cover crop. And the greatest yield benefit followed peas, oats, forage radish, and oats forage radish, as you can see in the table to the bottom right. So we showed that the significance of these results extends beyond our region in that when you fit the right cover crop with the right production system, you can really quantify the costs and the benefits. And you show that cover crops improve the farmer's bottom line. So when you only quantify the costs and benefits as sort of is traditionally done in that graph on the top right, it ends up looking like the cover crop mixtures are quite expensive. But when you quantify both the costs and the benefits in the table below, you can see that there are really measurable financial benefits following these cover crop mixtures. So the primary outcome of this research is the feasibility of increased sustainability in sweet corn production by integrating these winter-killed cover crop mixtures with no-till, and also broadening the benefits of cover crops to mitigate the environmental impacts of agriculture and increase farmers' profitability and grow healthy soil. Thank you.
Good afternoon, everyone. My name is Nico, and I'm a second-year graduate student at Cornell University at the Animal Science Department. My research concentrates on finding innovative and new management strategies for milking sheep year-round in short and frequent lactations. And for this presentation and the slide, I'd invite you to follow me from your left to your right, from top to bottom. For the past 1.5 years, we've been milking Finn sheep and Dorset crossbreed meat ewes at Cornell campus. And you might ask, why are we milking meat ewes, right? There's a reason. Meat ewes are seasonal or aseasonal polyestrous. They can breed and lamb year-round. And that is very different to the traditional dairy sheep. The traditional dairy sheep, the East Frisian sheep or the Lacan sheep, are seasonal polyestrous. They are being bred in fall and they lamb in April. They have one 180-day lactation per year. And that means that the US dairy sheep industry is a very seasonal business, right? There's no milk, no fresh product available for a good part of the year. And that, of course, is detrimental for the economic viability of small-scale sheep farming communities in the US, but in particular in the US Northeast and in New York State, which is my area of interest. And because of that, for the past 1.5 years, we've been collecting a vast amount of data And we've been analyzing a vast amount of data to sort of figure out a blueprint management system and guidelines, best management practices to milk sheep in short and frequent lactations year-round. And we have these used on a dietary trial. We investigate optimal dietary fiber levels, and we're also looking at milk yield, rumen pH, volatile fatty acid composition, energy balance, and blood NEFA. We're looking at milk composition, conception rates, prolificacy, all to sort of determine how do sheep have to be managed under such an intense system to be highly productive and yet remain optimal body condition scores, optimal health, high prolificacy, high lamb crops, and overall a good condition. We're doing this because we're trying to support our small-scale dairy farming communities to become more resilient through being more economically sustainable. Of course, if these farming communities milk their sheep year-round and produce milk year-round, they have product to sell year-round, which leads to more stable and a higher income. And it also has the advantage that these farming communities can use their technology year-round. They can use their milking parlors and their aging facilities, for example, year-round. And yeah, and the other advantage in that system is that New York State, the Southern Tier, and the US Northeast has millions of idle forage acreage available for grazing that is not utilized currently. And these idle forage acreages could also be utilized by small-scale sheep dairy farmers that milk their sheep in such a new system. And with that, I'd invite you to my poster tomorrow if you have questions about data and more details, and I hope I gave you a little bit of a insight into what I mean when I say milking sheep year-round in short and frequent lactations. Thank you.
Good afternoon to all. Today I will give you an overview of my research. So basically, I use probiotics to control salmonella and various pathogens, and also as growth promoters in chicken. So a modern day broiler weighs around 5 pounds in 5 weeks, while it was only around 2 pounds in 1960s. So have you ever wondered what are the factors that contributed this high level of achievement? So there are two major factors. The first one is genetic selection. So we basically selected the best performers as breeding stock. The second factor is nutritional interventions. They especially the use of antibiotics as growth promoters. So we have been using antibiotics as growth promoters, especially in feed, to enhance the production performance. So basically, it will reduce the subclinical infection and thereby promote the growth. So when we started using a lot of antibiotics in the feed, it has caused the emergence of more and more multi-drug resistant pathogen in the field, and it is very serious concerns to humans as well. So because of this increased antibiotic concern, the new veterinary feed directive bans the use of antibiotics as growth promoter in livestock production. Now we need alternatives. So probiotics has been used as alternative growth promoter in various studies, and they have shown to be promising in broiler production industry. So there are a lot of studies that have used probiotics in the feed, but it is also very important that the modern day broilers, they lack the contact with the adult hen during the incubation. And we all know that the microbiome, the contact with the hen results in the microbiome development, and it is very important for the production and growth in the chicks. So I discovered this project, it was a very accidental discovery. Basically, I was trying to control salmonella infection in chicken by spraying, dipping, also air sac inoculation. And I noticed something interesting, that all the eggs treated with the probiotics were bigger than the control group. So I sprayed the probiotics onto the embryonated eggshell without any inoculation or just spraying with atomizer using an airbrush. And after 21 days, when they hatched, they were kind of little longer and bigger than the control group. And then we continued supplementing the probiotics in the feed, and by 5 weeks, the birds were bigger and they have a really good ready-to-cook weight. significant difference was there. And more importantly, the feed conversion ratio was enhanced, which means that they required a lesser amount of feed to gain more amount of weight. So if the feed conversion ratio is 2, that means that we had to provide 2 kilograms of feed to gain 1 kilogram live weight. Feed conversion ratio 1.8 means we just have to provide 1.8 kilogram. So with the probiotic supplementation, the FCR was, feed conversion ratio was significantly lower, and the body weight was significantly higher. So with this, I conclude that we could use probiotics as early as possible, like during the day of incubation, as well as in the feed, to promote growth and development in broiler chicken. Thank you all for your attention.
After a long day at work, many people like to grab a glass of wine for a rest and enjoying their time with families and friends. More than 90% of local wines are produced from on the western coast side. Unfortunately, these areas are facing with water drought due to unstable climate patterns, leading to a decrease in production of wine. Washington State is the second largest premium wine producer in the United States, with total economic impact of $2 billion in 2016. We have 14 American viticultural areas, which are designated regions for wine production. Most of them are located in central Washington with around 8 inches of annual rainfall, making irrigation and water rights of paramount interest to the Washington wine industry. Traditional surface irrigation causes moisture loss associated with water evaporation and encourages weed growth. Here we introduced our first generation of direct root zone irrigation system, which delivers the water directly into lower root zones through vertical tubes. By collaborating with local growers and students, this project aims to evaluate the efficiency of irrigation system and try to find the optimal irrigation depths with a minimal amount of water use to improve water use efficiency and evaluate the health of grape wines on the different level of water stress. We currently have 3 major findings. First, irrigation depth has no significant effect on grape yield, but influences root distribution, which provides potential to lead root into deep soil and enhance water resistance of grape wine. Second, moderate water stress enhances grape quality and water use efficiency. We use and compare with commercial yield and rate. We produced 70% to 90% of grape yield by using around 60% of water through this direct root zone irrigation system. Third, compared with the surface irrigation, direct root zone irrigation system improved photosynthesis rate with optimal carbon allocation, which provide more carbon for grape wines for their vegetative growth and fruit production. We think this project will help lead to a better understanding of grape wines under water stress, help save water, and monitor the health of grape wines under water stress. I will have a poster presentation tomorrow, and my post number is 42. I'd like to welcome everybody to come by and discuss more about details about this project. Thank you so much.
Hi. Growers of winter squash for edible seed production in Western Oregon have been dealing with significant yield reductions over the last 20 years. Their fields have been plagued by disease symptoms that seem to be those of a soil-borne disease problem. Things like root rot and crown rot, vascular discoloration, and a devastating mid-season wilt. Because of these growers' concerns, a Western SARE project was developed in order to determine why all the winter squash were dying, and if we could identify this disease, how might we manage the problem? I'm a plant pathologist, and so I came into this project focused mostly on the diagnosis side of things. And we determined that this disease problem is caused by 3 to 5 different fungi working together to rot our winter squash plants. In order to get to this diagnosis, I collected fungal cultures from diseased and healthy winter squash plants. I created a disease rating scale in order to determine how severe this disease was. We surveyed the entire production area to see the distribution of these fungi, and then we ran fungal community analyses to identify significant fungi related to our disease symptoms to better inform our large-scale pathogenicity trials. Once we had a better idea of what exactly was involved in this disease problem, we were able to look at management techniques. So I evaluated the host range of cucurbits grown in the Western Oregon region, and we found some resistant germplasm for future breeding efforts. And we also looked at deficit irrigation and crop rotation as viable management strategies. We reached out to over 200 organic and conventional growers to educate them on this disease problem. And there's no viable chemical controls, so conventional and organic producers have the same set of tools for management: crop rotation, water management, and using resistant varieties which may not be desired by their specific markets. So soil-borne pathogens are the great equalizer, and this conversation between organic and conventional growers, we were able to enable that dialogue and get them communicating and sharing their different experiences. Ultimately, we've educated our growers on this disease complex, and we're working with them to develop specific disease management plans so they can be economically and environmentally sustainable in their winter squash production. But through this whole project, we were reminded of something that a lot of people have touched on today. When we're looking for sustainable answers, we really have to think holistically about our crop system. You can see that we had to go through many different paths of thought and experiments in order to get to our answer. And so I challenge everyone to continue thinking holistically when we're answering these complex problems of sustainability. And I will also have a poster tomorrow. Thank you very much for your time.
All right, so integrated approach to Medusa head rye grass control. Medusa head rye is a highly invasive winter annual grass that overtakes native vegetation. It also reduces livestock grazing densities by greater than 50%, all the way up to 80%. It's a big problem. So what our research entails is this bottom-up or tiered approach to control this grass. Now, I'm not Medusa head rye. I'm not just talking about Medusa head rye. This can also be implicated into other annual grasses. So the first part of this is herbicide application. So we use a non-selective herbicide, glyphosate, so Roundup, and what we found was cattle have a clear preference for glyphosate-treated annual grasses. They will consume it to the ground. So when we apply it, we're actually killing the grass, but we're also pausing the growth of that plant and providing longer durations of grazing. So that's the first tier. The second tier is biomass removal. I talked about cattle having a preference for that. Well, they will. They will go in and graze it. Not only will they graze that, but they will graze the thatch accumulation that smothers your native plants. So once they've cleared all the biomass from that area, the cattle themselves act as a soil disturbance. What that soil disturbance does is it's seedbed preparation. So before I go into the fourth tier, which is revegetation, these first three, the only input is the glyphosate so far. Ranchers have been doing this all along, except they put glyphosate down. That's the only input. They don't have to change anything they're doing already in the grazing landscape. Revegetation is pretty technical depending on area. So you've got to be very selective in your seeds, when to plant, how dense to plant. But the key thing is getting something in there that will compete against Medusa head. So that covers the 4th tier. After the 4th, you let those grasses come back the following year, and then you assess what you need to do for future restoration efforts. Our suggestion is to use residual herbicides, because once you have the desired vegetation there, you can use those residual herbicides without any effect on the seedlings. If you use it before, the seedlings die. So you'll have to come back in and do additional control, but the more of these tiers you use to control Medusa head and other annual grasses, the more control you're going to get. It provides a sustainable approach for producers with minimal input to revert the infested rangelands back into a sustainable format to where they can be profitable. Thank you.
So I kind of feel like I need to stand up here holding a chicken and grinning like a lunatic so you guys recognize me from the program. So you can decide I'm holding a chicken. Anyway, my NC SARE graduate student grant project is examining alternative cropping systems for organic vegetable growers. Specifically, I am looking at integrated crop rotations with chickens, whereby we're integrating slower growing breeds of chickens either directly into harvested vegetable crop residue or integrated into a cover crop that is following that spring vegetable. I think this project is very significant to sustainable agriculture because many of our current agriculture systems are actually very specialized. And with that specialization, we have seen a lot of benefits such as increased efficiency and increased yields and increased profits. But there have been some negative side effects to some of this specialization as well, such as the reduction of biodiversity on the farm or contamination of sensitive ecosystems from runoff and leaching. And I think that's where integrated systems come in. I think they have the benefit to address some of these challenges, such as reducing off-farm inputs and increasing the diversity of the farmer's income stream, increasing pollinator habitat and aiding in pest management, as well as just reducing farmers' risk and the increased economic resiliency of the grower and the farm. Additionally, organic growers are constantly balancing, having to adhere to organic principles, as well as increasing and maintaining farm profitability. So switching from more specialized to integrated systems can address some of these challenges by anyway, so the project that I am working on, I think some of the outcomes I want to address are the knowledge gaps that are associated with implementing integrated systems, specifically the day-to-day knowledge needed for raising slower growing breeds of chickens in an alternative production system, as well as we want to look at different cover crops that can work well in an integrated system that can double as poultry forage, as well as build soil health. We want to figure out if these systems can reduce off-farm inputs and do this by implementing economic analyses to determine if these systems are economically feasible. And finally, we want to increase grower knowledge of implementing these systems, and then hopefully increase vegetable grower adoption of integrated systems, not just in the north central SARE region, but nationwide as well. Thank you.
Good afternoon, and thank you for coming. The goal of my research was to evaluate the effects of cover crops used in organic sweet potato production on both plant health and sweet potato yield. As you may know, sweet potatoes are an important global food crop, with the United States ranking 10th in production. And in recent years, there has been an increase in the demand and the consumption of sweet potatoes, more so for especially for organically produced sweet potatoes, as consumers become aware of how their food is produced. The organically produced sweet potato demand production is, however, well below demand due to various challenges such as weeds and soil-borne diseases such as Fusarium root rots. Weeds will directly impact the yield of the sweet potatoes, whereas Fusarium root rots will influence the quality of the sweet potatoes and will result in high post-harvest losses because these will normally be manifest in storage even though they will infect your plants in the field. Cover crops have been proposed in several studies to be a viable option for not only suppressing weeds, but also suppressing soil-borne diseases and improving overall plant performance. And so this led us to conduct this study in collaboration with a certified organic farmer based in Marshall, Missouri. And in our study, we used two cover crop species, namely rapeseed and cereal rye. So we used this either as a cover crop, in which case residue was left on the surface after termination, or as a green manure crop, in which case the residue was stilled into the soil after termination. Both cover crops were planted in fall of 2016 and terminated in spring of 2017 prior to transplanting the sweet potato slips. And once we transplanted the sweet potato slips in June of 2017, we monitored the plots for percent weed cover, which data is shown in the graph on your far left. And we also monitored the plots for the plant vigor. So we were trying to determine how well the sweet potato plants looked in each plot. And at harvest, we determined the yield. So the total yield and the marketable yield, which would be the tubers that could be sold based on the USDA grading standards. And as you will see in the graphs below on the slide, we noticed that regardless of whether we used rapeseed or cereal rye, basically the plots that had these two cover crops incorporated into the soil as a green manure resulted in the least amount of weeds and healthier sweet potato plants, which translated into higher yields as well. And so hopefully this will help us to develop a strategy that we can share with organic farmers, especially to address some of the challenges they face. I will have more to talk about this in my poster session tomorrow, and you're more than welcome to attend this. Thank you.
Hi, I'm a doctoral candidate in cultural anthropology at Emory University in Atlanta, Georgia, and I am presenting findings from an aspect of my dissertation research on the livelihood strategies of beginning farmers in Iowa. So this facet of my project started with conversations that I had with young farmers during my pilot study in summer 2014. Everybody was generally interested in what the challenges facing beginning farmers were, but everyone was also basically in agreement that those challenges were access to land, access to capital, and access to equipment. A more interesting question came up when we started talking about the group of beginning farmers who had overcome those initial barriers to entry and asked what differentiated the farmers who stayed in it long-term from those who decided to stop farming after a couple of years. The question became, what does it really take to make it in farming long-term? To address this question, I interviewed 14 people from 12 farms who had decided to stop farming within their first 5 years. Like the 52 beginning farmers in the rest of my broader dissertation project, these had been people primarily running small-scale, diversified farms targeting local markets. I was particularly interested in the relationship between profitability and longevity. Did only profitable farms make it, and did unprofitability inevitably lead to farm closure? In my sample, this turned out not to be the case. Of the 12 closed farms whose owners I interviewed, 4 had been not profitable, 1 had been breaking even, and 7 had been running profitable operations. Indeed, the most profitable vegetable farmer that I ever worked with, someone who was grossing over 6 figures and netting a comfortable profit by her 3rd year, decided to stop farming after that 3rd year. And on the flip side, I talked to many beginning farmers who weren't yet breaking even, but who were still and are still farming. Of course, the decision to stop farming is complex and multi-layered, but after analyzing my interview transcripts, I did my best to distill everybody's story down into one big reason to answer the question, why did you decide to stop farming? In my sample, family stressors turned out to be the most common reason given. So I talked with one couple who had been running a successful small farm together. They were profitable, and it was taking a toll on the marriage. And one of them told me, quote, "I'm committed to the marriage first, any business endeavor second." I also talked with people who decided to quit after a divorce, people who had non-farming partners who were kind of fundamentally unsupportive of the farming project, and people who cited irreconcilable differences with their parents or with their in-laws. Of course, farm finances are also important, and 2 people did indicate that not making enough money was the primary reason that they decided to stop farming. Making it in farming should mean being able to stay in agriculture as long as you want and be able to pay yourself fairly. Profitability is obviously critical to this goal, but in my group, it seemed insufficient to ensure a new farm's long-term viability. Whether or not a new farm makes it cannot be boiled down to a simple yes or no question of profitable or unprofitable, but rather seems to be contingent on a whole constellation of factors, both social and financial. My hope is that reflecting on these findings helps beginning and aspiring farmers and those who mentor and advise them to broaden out their definition of farm economics to include also the kinds of variables that can't easily be represented on profit and loss statements. Thank you.
It's easy to romanticize our results. When you begin publication and output of your findings, or even just a grower presentation, this is where you start. Click to add text. And today I want you to take home a message of click to add content. SARE is all about creating content, not content about the short term, but the long term. My findings from my research project lead me to this slide because my research project worked with harlequin bug. Harlequin bug is a persistent pest of cole crops, particularly in the southern United States. And most vegetable growers know this bug is a notorious sort of outbreak pest that comes from nowhere. When I was working with vegetable growers in Maryland, I actually had a chance to work with a conventional grower, an acreage of about 100 acres. This was just sort of passively, the benefit of working with entomology is you get to field collect. So anytime you come across a grower with a load of bugs, you're right there overnight. And one of the things working in mustards, I was able to talk with a grower about other mustard options. And we might be familiar with the biofumigant mustard, right, as something that's been developed. This grower was also familiar with biofumigant mustard. The biofumigant mustard he was instructed on by some grower meeting that this is a great option for controlling wireworms. And he turned to me and he said, "Tony, I've got wireworms that are destroying my corn. For some reason they're attacking my sweet corn. I don't know what to do. I have this stuff in the shed that's illegal, but I don't know what to do." It's like, well, I'm not sure if the biofumigant mustard's going to work. He's like, "Yeah, it didn't work. I put it the season before. I don't know. Someone told me to put biofumigant mustard. Now I have wireworms taking down my sweet corn." He pulled the trigger on the illegal product. When we create content, that can affect decisions on the farm. And we need to be aware that when we're creating a new technology, a new product for a grower, or new method of control, especially in pest management, that there are no silver bullets. We need to think of the long term, the continuity of each project leading into another. And then that's why SARE meetings like this are really important, so we can understand the continuity of each project and how it envelopes with each other. My project, yes, it found the obvious. We found that harlequin bugs like the color green, their host plant is green. We found they like the smell of their host plant. And we found that they love the aggregation pheromone that they all produce. And yes, you can put this on an artificial stimuli and create a trap. My project essentially helped create a trap for a harlequin bug, but that's not the silver bullet for management. The silver bullet is looking further past the trap. Going back to the mustard, we actually are developing a mustard trap crop that will hopefully one day emit aggregation pheromone, creating a super attractive trap crop. But that doesn't stop there. And with SARE, it's all about continuing the projects that lead into one another. And understanding where we start is where we click to add content. Thank you.
We all know that different people have different eating styles. Some people like sweet. We will put more sugar when we cook for them. Some people like spicy, so we will put more pepper in their food. But do you think plants also have different eating styles too? Imagine you are a peach grower and you have different kinds of peach trees. You have early season peach tree, which harvests in May, and then you have late season peach tree, which harvests in September. Do you think that these different kinds of peach tree, they will have different demands for nutrients? Do we have to fertilize them differently? You may want to ask me this question. Why do we care about this? We can just apply lots of nutrients and make sure every tree is happy. Well, think about this. If all the growers apply lots of nutrients to their orchards, how much environmental pollution this will cause? Besides, if we apply too much nutrients to the peach tree, they will grow too many branches and leaves, and it will increase the labor cost for pruning. And they are having so much fun for growing all the branches and leaves that they forgot to have babies, which means they will have less fruits and the yield will decrease. So our project is to help the farmers to fertilize the peach tree more reasonably, enough but not too much. We selected 18 trees from different ripening seasons and measured how much nutrients have been lost each year through pruning, thinning, harvesting, and leaf fall. And what is thinning? Thinning is in the spring. We remove some tiny little fruits, trying to make sure those remaining on the tree can grow bigger. We find that early season peach tree can last more calcium, while late season peach tree can last more phosphorus and potassium. And that indicates different season peach trees do have different eating styles. Early season peach tree like more calcium in their food, while late season peach tree love a buffet with more phosphorus and potassium. We have a strong belief that our research could help the farmers to optimize the peach fertilization based on what kind of peach trees they have, and to reduce environmental pollution as well. Thank you.